Hi everyone. Today we will discuss Module 5 Nanotechnology and Quantum Computing, which is from Physics for Computer Technology course. In this session, we will focus mainly on nanotechnology, its definition, importance at the nanoscale, properties of the nanomaterial, and fabrication methods. This we will discuss in this video lecture. In this module, we will look at what is nanomaterial, what makes the nanoscale interesting, the concept of surface to volume ratio, the physical properties of nanomaterials, and finally, uh, let us see the different fabrication methods. Now let us see what is nanomaterial. Nanotechnology is the understanding and the control of materials at dimensions of roughly 1 to 100 nanometers. At this scale, unique phenomena enable novel applications. To remind ourselves, a nanometer is 1000 millionth of a meter. Richard Feynman first pointed out the possibilities in his famous 1959 talk. There is plenty of room at the bottom at the American Physical Society. Now let us see the optical properties. Actually, uh, gold is a striking example. Bulk gold appears yellow in color, but nano-sized gold appears red. At a nanoscale, electrons are not free to move as they do in bulk gold because this movement is restricted. Light interact differently. The color actually depends on the particle size. Quantum dots of 3.2 nanometer show blue emission. Quantum dots of 5 nanometer show red emission. Gold clusters of 12 nanometer also appear red. Now let us see the surface to volume ratio. As particle size decreases, the surface to volume ratio increases. This can be shown in this diagram. Here we can see in one beaker we can takes the balls. In another one we can take the fine powders. So this is the example for bulk material and nanomaterial. This means more of a substance come into contact with its surrounding in the nanomaterials. As a result, nanomaterials often act as better catalysts since a larger proportion of atoms are exposed for reaction. To illustrate surface to volume ratio, consider a cube of side 4 centimeter. Its surface area is 96 centimeter square and the volume is 64 centimeter cube. Now, if we divide it into 8 smaller cubes of 2 centimeter each, the total surface area doubles to 192 centimeter square. Through the volume, uh, though the volume remains the same. This shows how reducing particle size increases the surface exposure drastically. So, which is exactly what happens at the nanoscale. Now let us see quantum well, wire and dot. We can also classify nanostructures by their confinement. In quantum well, electrons move only in two dimensions. In quantum wire, they move only in one dimension. In quantum dot, electrons are confined in all directions. Three-dimensional called three-dimensional confinement. When size drops below 100 nanometer, properties change dramatically. If one dimension alone is reduced, we can get well. If two, we can get wire. If all three, we can able to get the quantum dot. So this is about the quantum well, wire and dot. Next, let us see the physical properties of nanomaterials. Nanomaterials display special physical properties. They are reduced melting point due to more surface atoms. Ultra harness with the mechanical strength approaching theoretical limits. Optical properties very different from bulk. Electrical conductivity may decrease due to surface scattering, but can also increase due to ballistic transport. Magnetic properties uh, will be changed. Ferromagnetism may disappear, giving supermagnetism. Self purification occurs with a defect migrating to surfaces. And importantly, most properties of the nanomaterials are tunable with the size. Now let us see the fabrication methods. To create nanomaterials, uh, we use two main approaches. One is top-down approach and another one is bottom-up approach. Top-down approach is nothing but breaking down bulk materials into nanoscale structure. Example, lithography, ball milling. Bottom-up approach is assembling of atoms or molecules into nanoscale materials. Example, sol gel, chemical vapor deposition. There is also a hybrid method combining both approaches. Each method is chosen based on whether precision, cost, or scalability is most important. Now let us see the classification of synthesizing methods of nanomaterials. Nanomaterials can be synthesized by physical methods. They are further classified into ball milling, vapor phase deposition, lithography. And then chemical methods. This can be classified into sol gel, colloids, microemulsion. And then biological methods using biomembrane, DNA, or enzymes. Notice how interdisciplinary nanotechnology is. It uses physics, chemistry, and even biology to build advanced materials. Now let us see the ball milling method. Actually, the ball milling method is a mechanical process used to produce nanomaterials. A ball mill consists of stainless steel container as shown in this figure, inside which small balls of materials like iron, hardened steel, silicon carbide, or tungsten carbide are placed. These balls rotate inside the drum and crush the powder material placed in the container. To enhance milling energy, a magnet is placed outside the container, which applies a pulling force on the material as the chamber rotates. Typically, the ball to material mass ratio is kept at 2:1 ratio. During milling, the balls impart very large amount of energy to the powder, breaking it down into nano-sized particles. The process usually runs for 100 to 150 hours to achieve uniform fine powder. So this method have some advantages also. Nano powders in the range of 2 to 20 nanometer can be produced. The final size depend on the speed of ball rotation, and then the cost of this method is very minimum. And then next we are going to see the now with this I am concluding this session. Actually, nanotechnology deals with the structures in the 1 to 100 nanometer range. Properties like optical, electrical, magnetic, and mechanical change dramatically at a nanoscale. Surface to volume ratio plays a key role in enhanced reactivity. Fabrication methods range from top down to bottom up approaches. Nanomaterials are paving the way for next generation electronics, medicine, and quantum computing. Thank you for watching this video. In further coming videos, we will discuss about other fabrication methods. Thank you.